Hey everyone. I decided to put together like a little review session where I'm just gonna run through the review sheet that is posted up on Mastering Chemistry. I would recommend not sitting down to watch this video and watch me work through these problems until you try to do it yourself. Basically, you want to be able to do this on your own, okay? You don't want, you want to be able to sit down on exam day and be really comfortable working through all these types of questions. But certainly, if you don't know how to do something, it's frustrating to sit there and just stare at a piece of paper. So we'll try to take care of some of that, right? So we'll just go through question at a time. Question number 1, true or false, NO is an ionic compound. To figure out if something is ionic or molecular, what do? You figure out whether the components are metals or nonmetals. Okay, so here we have nitrogen, that's a nonmetal, and we have oxygen, which is also a nonmetal. When you have two nonmetals, that does not form an ionic compound. That forms what's called a molecular compound. Okay, an ionic compound would have a metal and a nonmetal present. All right, so question number 2 then. Reactants can be gases and liquids. Sure, why not? Reactants can be solids, liquids, gases, or in aqueous solution, as can products, right? Number 3, we're talking about a combination reaction. Okay, so this question and the next question. The type of reaction is described by the title of it, okay? So a combination reaction. You would look to see if 2 or more reactants form one product. So in a combination reaction, you would have A and B, and it would come together to form your product. So they're combining here to form C. So that's true. That is the definition of a combination reaction. What's pretty much the reverse of that reaction would be what's called a decomposition reaction. Okay, so in number 4, it asks about a decomposition reaction. So you would look to see if one reactant forms 2 or more products. Okay, it's decomposing to form multiple products. So number 4 is true as well. Number 5, true or false for the compound lithium chloride, the chloride ions are cations. All right, so let's look at lithium chloride. We would have lithium and chlorine. Lithium has a +1 charge because it's in group 1. Chlorine has a -1 charge because it's in group 7. So now you're deciding which one here is the anion and the cation. So we do that based on whether the charge is positive or negative. The positive charge, that's the cation. The negative charge, that's the anion. Okay, so the chloride ions are anions, they are not cations. All right, name the following anions. H, C8, Cl, C. Okay, so you're going to take all these compounds, you're going to turn them into their anion forms and then name them. All right, because they're not, I don't know, maybe it's just on mine that you can't see the negative signs. They should be there. My computer screen's kind of small though, so I'm going to hope that you guys see this. And Cr042-. So you just want to go through and name these guys, right? So if you have a hydrogen anion, you're going to take the root of it and add the IDE ending. Okay. Same thing for chlorine. Take the root of it and add the IDE ending. This right here is a polyatomic ion, which you have to know the name, formula, and charge of. That's the acetate ion. And this right here is the chromate ion, also another polyatomic ion that you need to know. Okay. Write and balance the equation for the reaction between liquid cyclohexene and oxygen forming carbon dioxide and water. This is probably a little more complicated than you're going to have to do in terms of pulling formulas out of a name like that. But you should be able to figure out what the formula of everything would be, all right? I'm going to give you the base for this. If you weren't able to do this problem because you couldn't figure out like what cyclohexene was, that's fine. I don't think you're going to have to memorize that, okay? So you can start at least by knowing that. You should be able to, you should know by now that oxygen gas is going to be O2, okay? And then it's going to form CO2 and H2O. All right, so I know that you can't see that whole thing on the board, but I'll try to like bring it closer together as I work. So where do you start here? You want to start with the thing that is most complicated, okay? So probably your C6H10. You know, we talked before about keeping track of this stuff. So we've got carbon, hydrogen, oxygen, 6, 10, 2. Oops. Right, so that's our breakdown right now. And the first thing I guess you could try to fix is this carbon discrepancy, right? So maybe we'll rewrite this equation up here. And we'll put 6 CO2s there, okay? Now you've got 6 carbons, and now you've got 12, 13 oxygens. You already know that this is going to be annoying because you have this odd number of oxygens here, all right? But we'll get to how we deal with that in a minute. So carbons are okay. Let's look at these hydrogens. We have 10 hydrogens over here. We have 2 over here. So I am going to fix this water molecule so I can make my hydrogens the same at least. So I'm going to put a 5 in front of my H2O. So now I've got 10 hydrogens, and now I have the 12 oxygens that were from the CO2, and I have to add 5 more to that. 17 oxygens there. Sorry. And now everything is the same except my my oxygen, okay? And I can't change this O2 molecule to something that's going to match the oxygen on my right-hand side because this is an odd number and this is an even number, right? So this is a situation where we were kind of discussing in that lecture chat where I would recommend if you are in this situation where you have an O2 molecule up here and you're working with an odd number of oxygens down here, you take this current balanced equation, kind of not including the oxygen because you're going to have to alter that, but multiply the rest of it by 2. Multiply every other coefficient by 2. Okay? Because when you do that, you're going to end up with an oxygen value over here that's an even number. And then you can alter the coefficient in front of an O2 molecule to give you back the even number that you need. All right, so now if you end up with 2 C6H10, plus, we're going to just leave a blank in front of that O2 for now, yields 12 CO2 plus 10 H2O. Okay. Let's see what our tally looks like. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. So now we have 12 carbons over here. We have 12 carbons over here. We have 10 times 2, 20 hydrogens here. 10 times 2, we have 20 hydrogens here. Oxygen, we have 12 times 2 is 24, plus 10 is 34. Now we use this number to decide what our coefficient here is going to be. So 34 divided by 2 is 17. That is the coefficient that goes in front of our oxygen. And that is our balanced equation. 2 cyclohexenes, 17 oxygens, yields 12 carbon dioxides and 10 waters. Okay? All right. Next question, number 8. Balance the following equation and name each compound. So we have Mg3 and 2. I'm not including the states here just to save space, but don't do that when you're actually writing out these formulas. Plus H2O. Okay, so let's start by balancing. You've got magnesium, nitrogen, hydrogen, and oxygen. Right, so right off the bat, I'm looking at Mg3 and 2 and MgOH2. So I am going to put a coefficient of 3 in front of that MgOH2 and, oh, I didn't put my tally in. Hold on, let me do that real quick. 3, 2, 2, 1, 1. Okay, so hopefully that makes sense to you where all that came from. So now I've changed my coefficient in front of my magnesium hydroxide. So now I've got 3 magnesiums and I have 2 times 3, 6 oxygens. And I have 2 times 3 is 6 hydrogens, 6, 7, 8, 9. Right? Right. So what next? All right, I've got this coefficient of 2, or the subscript of 2 rather, over here next to my magnesium. So why don't I try to balance that out over here? Put a 2 in front of there and see how it changes things. All right, now I've got 6 hydrogens over here and 6 hydrogens over here. So now I've got 12 hydrogens over here. All right. Now I'm going to go back to the reactant side of my equation where I see this hydrogen and oxygen discrepancy down here. I've got 12 hydrogens over here and I've got 2 on my reactant side. So what can I do to this water molecule to sort that out? I can put a coefficient of 6 in front of that H2O. Now I've got 12 hydrogens and I've got 6 oxygens and everything is balanced out numerically. Okay. So let's write that out a little less sloppy. Start here. G 3N2 plus 6H2O, 3Mg OH2 plus 2NH3. Okay. And now we want to name everything that's in here. So to name things, you have to decide what kind of compound it is first. Okay, so we'll start with the first compound here. Is it ionic or molecular? That's the first question you have to ask yourself. Hopefully it's clear that the magnesium here is a metal, the nitrogen's a non-metal, so that's an ionic compound. The next question you have to ask yourself is what type of ionic compound is it? The magnesium has a charge that doesn't change from compound to compound. It always forms an Mg2 plus ion. That means that it's type 1. So we're going to put the name of the metal. And we don't need to indicate its charge because it's a charge that doesn't change. So now we can just name the anion after it. Okay, so we take the root of nitrogen and then add the IDE ending to it. Okay, we all know that this is water. Water is a molecular compound because it's made of 2 nonmetals. So if we were going to name water in the IUPAC manner, there's 2 hydrogens here. So that's dihydrogen monoxide. All right. MgOH2 is another ionic compound. Magnesium, still a metal, and OH minus is a polyatomic ion that you need to have memorized, right? That's the hydroxide ion. So to name this, it's the name of the cation, and then the name of the polyatomic anion. So it's magnesium hydroxide. And again, we don't have to indicate the charge here because magnesium is always a 2+ cation. NH3, that is ammonia. That's a common name that you should know. You want to be able to recognize that formula when you hear or read the word ammonia. But I don't know, maybe as a fun exercise, you guys could figure out the molecular name for it. I guess the less common name for it. I'll leave you guys to think about that. All right, next question, number 9. Math question now. How many moles of magnesium hydroxide are produced from 0.319 moles of magnesium nitride? And we're going to use that balanced equation to figure out the answer to this question. All right, that's why we spent some time balancing it. So you set up these questions the same all the time. How many moles of MgOH2 equals 0.319 of Mg3N2. Okay, now you're going to multiply this by a conversion factor. Okay, whatever number you're given with, whatever you start with, that goes on the bottom of the fraction bar of your conversion factor. Okay, so we know that we're putting Mg3N2 on the bottom of our conversion factor. We're going to look to the balanced chemical equation to see what our number values are. So if you look at that balanced equation, you see that every 1 mole of Mg3N2 produces 3 moles of MgOH2. Okay, it's a 1-to-3 ratio. So then we see that our moles of Mg3N2 are going to cancel out. We multiply that across, and it gives us 0.957 moles. Okay. Next question is very similar. Let me just grab a different marker. All right, how many grams of water are necessary to produce 4.39 moles of ammonia? All right, so oh, 4.39. Okay, so our first conversion here, moles of ammonia is going to go on the bottom. And we're going to use our number from our balanced equation to fill this value in. Okay, that number comes from our balanced equation. Now we're looking for the relationship between water and ammonia here. So we have 2 moles of ammonia is equivalent to 6 moles of water. So now we've essentially switched from ammonia to water. And I want to know how many grams of water, so I'm going to have to multiply that by the molar mass of water. So I know that 1 mole of H2O is 18.02 grams of H2O. Okay. Now everything that's on the top of the fraction bar gets multiplied. Everything that's on the bottom gets divided. You should end up with around 237 grams. Okay, if 12.48 grams of MgOH2 are formed, let's write that number down just to start with. 12.48 grams MgOH2. How many grams of ammonia are produced? All right, so if we're drawing out like our conversion factor chain here, we're relating magnesium hydroxide and ammonia now, right? So the first thing you have to do is go from grams of MgOH2 to moles of MgOH2. Once you've gone from grams to moles, now you're going to go from moles of MgOH2 to moles of ammonia. Okay, and this comes from the balanced chemical equation. Once you've converted to moles of ammonia, your next step is going to be going from moles of NH3 to grams of NH3. So we need to do some molar mass calculations to figure the rest of this out. So MgOH2 just bear with me while I do these calculations. Okay, I got 58.32 grams per mole for MgOH2. For ammonia, (17.03). And this part is our balanced equation. Okay, that's what's going to fill in our values over there. So you look back and you're like, all right, well, for every 3 moles of the MgOH2, 2 moles of ammonia. All right, so in your calculator, your math should look like 12.48 times 1 times 2 times 17.03 divided by 58.32 divided by 3 divided by 1. right? And it should come out with like 2.430 grams of NH3. All right, that got a little bit messy. I'm gonna have to fix the height of this camera eventually. All right, next question. Predict the chemical formulas of the compounds formed by the following pairs of ions. All right, so you're making formulas from ions here. So you have Cr3 plus, and you have Br minus 1. So what do we say we're gonna do? Our first step, we're gonna do this little shorthand here. Whatever the charge, the numerical charge of the cation is, that becomes the subscript of our anion. Whatever the numerical charge of our anion is, becomes the subscript of our cation. Okay, so we have 1 chromium for every 3 bromines. So the formula is going to be CrBr3. Okay, if we have an Fe2 plus, an Fe3 plus is how this is. Yeah, 3 plus. An Fe3 plus and an O2 minus. That's going to give us an Fe2O3 compound. All right. Let's skip down to letter E, where we have NH4 plus, and we have PO4 3 minus. So you have to know the names of these ions and these charges, right? So you'd have to be able to name this compound that you're forming as well. So to start off with, we're going to do our swap here, and we're going to need 3 ammonium ions for every 1 phosphate. So our formula for this will be NH4 3 PO4. So notice that I have these parentheses around the NH4. That's because I want to indicate that I need 3 of the entire thing. Okay, I don't just need 3 extra sets of hydrogens. I need 3 ammoniums for every 1 phosphate. All right, so then you would name that ammonium phosphate. For the next question, you're looking down and running through to see whether these things are molecular compounds or ionic compounds. That just involves you looking to see if you're dealing with metals, non-metals. Anytime that you have a metal plus a non-metal, that's ionic. Non-metal plus non-metal, that's molecular. So you can run through and do those ones on your own. Name the following. All right, we can do some of number 14. Okay, you have a mix here of ionic compounds, molecular compounds, and acids. And so you have to be able to differentiate them before you can name them, right? So for this first one, you're looking at CaSO4. So right away, you have to be able to look at that and recognize that it's an ionic compound. Then you have to recognize the fact that calcium is a group 1 or a type 1 ionic compound. It always forms a 2+ charge. So when you're naming it, you don't need to include the charge in the name. It's just calcium sulfate, right? And the name sulfate comes from that SO4 2- polyatomic ion that you also have to know the name for. B, PF5, both phosphorus and fluorine are nonmetals. So this is a molecular compound. So we are going to name it using our prefixes, okay? We don't have to include the mono prefix in front of our first nonmetal, so we can just name it regular phosphorus. Oh, sorry, cut that off. But we do need to put a prefix in front of the number of fluorines that are present. There are 5 of them. So that will be pentafluoride. Okay, the root and the IDE ending is still kind of the same as before with the ionic compounds. All right, NaClO3. You're going to have to recognize that Na is a metal, and that ClO3 minus is a polyatomic ion. Okay, that means that we're dealing with ionic compounds. So, sodium is also a type 1 metal, so it's always going to have a +1 charge. So we have our sodium. Okay, and then ClO3 minus, that's the chlorate ion. So this is sodium chlorate, right? CO2, it is a molecular compound, 1 carbon, 2 oxygens, so it's carbon dioxide. H2SO4, now this is a big thing. So when you see that H out front like that, that should indicate to you right away that we're dealing with an acid and that you have to name it following the acid rules. It's not just a standard molecular compound. So the first question you have to ask yourself once you've identified the fact that it's an acid is whether it's a binary acid or an oxyacid. The presence of that oxygen right there tells you that it's an oxyacid. Then you have to remember that oxyacids are named solely based on the polyatomic ion that makes them up, okay? The polyatomic ions that have ATE endings are going to have IC acid endings. Polyatomic ions that have ITE endings are going to have OUS acid endings. And this one in particular is a special case because you would hopefully look at the SO4 2- and know that it's a sulfate ion. And then you'd want to name this sulfic acid, but this one is a special exception. It's really one of the only 2 exceptions for the acids that there are, so it's good that we talk about it. And this is called sulfuric acid. Okay, but you still see how it still maintains that IC ending. There's just an extra addition there. The root didn't get totally chopped off. Okay. Our last example here, CuCN2. Okay, so again, you're going to recognize first that it's an ionic compound because it has a metal and a polyatomic ion that makes it up. Then you have to say to yourself, copper. Copper is a transition metal. Copper has a charge that varies, all right? So when I name this compound, I'm going to have to indicate the charge of copper in the name of the compound. So you have to break this back up now, all right? Now, the CN you have to know exists as a CN-1, okay? If CN exists as -1 and there are 2 of them, that means that this copper has to be Cu2+. So it's a copper 2. So when you name it, you have to indicate that. So you have to call it copper 2 cyanide. cyanide. Okay. All right. Write the formula for each of the following. This is number 15 for people that are keeping track. Tin for, I'm just going to pick a couple of these ones. Tin for chloride. So when you're figuring out a formula from a name, you want to look at the, in this case, you know that it's an ionic compound because tin is a metal, and they tell you the charge on it. So you have to know the actual symbol for that element. Then the anion will be Cl minus 1. So you see when you put those together, you get the formula back from that. Okay. Let's see, what's a good one? All right, let's do C. I don't know about a good one, but that one looks annoying. So we might as well do that one together. Osmium 8 oxide. Okay. So when you are looking at something like this, again, you have to recognize that it's an ionic compound. This is a very good giveaway that you're dealing with a metal if you don't recognize the name of the compound as a metal and a nonmetal together, because nonmetals, we don't have parentheses indicating charges on things that are nonmetals. So you're only going to see this notation when you have a metal preceding it. So we know right here that we're looking at an osmium ion with a charge of 8. Okay. We know that every oxygen ion is going to exist as -2. Okay, so now we're going to do our little and we get OS2O8. But then we say to ourselves, no, I'm not going to leave it like this because I can reduce these. And I'm never going to leave an ionic formula in an unreduced form. So I can divide both of these numbers by 2. And when I do that, I get OSO4. All right. Let us move on. I'll let you guys do that. All right, I will balance, well, I already balanced. You guys should be able to balance these. Let's do number 19. What's the empirical formula of a compound such that 200 grams of it contains 87.2 grams of phosphorus and 112.8 grams of oxygen? All right. So what do we do with this? Okay. I mean, when we're looking at empirical formulas, right? We're not looking at mass values. We're looking at mole values, right? So when we have these two mass values that we're given, we have 87.2 grams of phosphorus and we have 112.8 grams of oxygen. The first thing we want to do is take these gram values and we want to turn them into mole values using our periodic table. Because once we have these mole values, then we can create a relationship between these two things. All right, so look up the atomic masses on your periodic table. We've got, let me do this one first. We've got 87.2 grams of phosphorus. There's 30.97 grams in 1 mole. And then okay. So those are our two equations that we want to set up. Okay, let's get numbers for this. Divided by 30.97. So we got 36.8. And oxygen by 16. Oops, that's not right. That's not right. It's no good when I don't have you guys here telling me that I'm doing my math wrong. 2.82. There we go. You can't even see that. Hold on, let me move this little guy over. Okay. So, all right, so maybe that's right. We'll see in a minute. So when we're doing empirical formulas, our next step after we get our mole values is that we're going to write our pseudo formulas. So that'll leave us with P 2.82, O 7.05, and we're going to divide both of these values by the smaller of the two numbers. Okay, so we get P1 and O divided by 2.5. Okay, now we can't leave it like this because we can't have a decimal. So we're going to take our whole empirical formula and multiply it by 2 so that we get a formula out that has whole numbers in it. So we get P2O5. Okay, that's our empirical formulas. All right, but we'll try another example of that since those ones are kind of important. So let's look at number 20. You guys can do A on your own, but let's do 20B. We have a compound that's 87.5% nitrogen and 12.5% hydrogen by mass. All right, so we know that when we're looking at things that are percent by mass values, that we're going to basically turn our percent value into a mass value. So instead of 87.5%, we'll look at that as 87.5 grams of nitrogen. And we'll look at this as 12.5 grams of hydrogen. And once we have gram values, then we immediately want to turn those into mole values. Okay? So we're going to use our periodic table. I know I'm doing this as like a grouped step here, but it's just easier for me. Let's see, now I can do all my calculator work. So 87.5 divided by 14.01 is 6.25 moles of nitrogen. And 12.5 divided by 1.008 gives me 12.4. For this. Okay. I hit clear before I got my decimal. Oh no, that was fine. Okay. And now I'm going to rewrite this. Okay. So I have N 6.25, H 12.4. I will divide both of these by 6.25. And I get N1 H 1.98. This number is roundable, okay? It's within 0.1 of a whole number. So you can rewrite this as NH2. All right. If it was 1.88, you could not do that. All right. Let's look at the next one. I don't want to do all of them and leave you with nothing to try on your own. Okay, let's do number 22 because that has empirical and molecular in it. Okay. And it's a combustion. So really gives us everything. Just erase. Right. So we have got a C, an H, and an O sample. We're going to combust it over an oxygen flame. And we're going to get carbon dioxide and water back out, standard for any kind of combustion. And specifically, we have a 0.1005 gram sample, and it produces 0.2829 grams of CO2 and 0.1159 grams of H2O. Okay, and we're also told that the molar mass of this thing is 156 grams per mole. Okay, so that's the information that we're given, and we want to know two things: what the empirical formula is and what the molecular formula is. Right? We have to answer both of those questions. So to figure out what the empirical formula is, I have to know the amount of carbon, hydrogen, and oxygen that I started with in moles. All right. I'm going to use my carbon dioxide and my H2O value to get me there. But I can only do that directly with the carbon and the hydrogen, not with the oxygen. So I will start with carbon. Okay, I've got 0.2829 grams of CO2. My first conversion is going to be from grams of CO2 into moles. Okay. And once I have converted from grams of CO2 into moles of CO2, now I want to convert from moles of carbon dioxide into just moles of carbon. So every 1 mole of CO2 has 1 mole of carbon in it. Okay, it's a 1-to-1 ratio. Just doing some calculator stuff now. So I get 6.428 times 10 to the negative 3 moles of carbon. All right. On to hydrogen, because I can do the same process for hydrogen. I've got 0.1159 grams of H2O. So I'm going to convert from grams of H2O to moles. And now over here, I have to convert from moles of H2O to moles of hydrogen. And this ratio becomes very important right here, okay? For every 1 mole of H2O, I have 2 moles of hydrogen. I have to make sure to take that into account when I'm doing this calculation. Now some calculator stuff. Zero, 1, 2, 8, 6 moles of hydrogen. All right. Now I need to find the same information for oxygen, but I cannot do it the same way because all of my oxygen that's present in my carbon dioxide and in my H2O, it's all been contaminated by this oxygen flame. So I have to separately find a way to figure out how much oxygen was present there. Okay, but I was given this value here, the initial sample mass. So I know how much my total sample weighed. So if I can use the moles of carbon and the moles of hydrogen, I can use those 2 values, then I can figure out how much oxygen was in my sample. But to do that, I'm going to have to turn these mole values of carbon and hydrogen into gram values so I can subtract them from my initial sample mass. So I'm going to take this value, my moles of carbon, I'm going to multiply it by the molar mass of carbon. And that's going to tell me how much. So I'm going to have this mole value here. That's the number that I'm putting in my calculator right here. And then I'm multiplying that by the molar mass of carbon. That's going to tell me how many grams of carbon came from my original sample. 6.428 times 10 to the negative 3 times 12.01. So my original sample had 0.07720 grams of carbon. Now I'm going to do the same thing for hydrogen. I'm going to take this mole value for hydrogen. I'm going to multiply it by the molar mass of hydrogen. Okay, so 0.01286 times 1.008 is 0.01296 grams of hydrogen. Okay, now I am going to go, right, I'm going to move this a little bit. So I'm going to go back up here. All right, I'm going to erase some of this stuff. I'm going to go back up here where I had my original sample. And I'm going to subtract my carbon mass from it. I'm going to subtract 0.07720. And I'm going to subtract my hydrogen, 0.01296. And I'm going to see what's left. 0.1005 minus 0.7720, 0.7720 minus 0.01296. And it turns out I have 0.010 0.034 grams of oxygen. Okay, that was in my original sample. Once I have a gram value for oxygen, now I can calculate its moles. All right, so there's 16 grams of oxygen in every 1 mole. So I'm going to multiply that value. So 0.01034 times 1 divided by 16. And my mole value is 6.4625 times 10 to the negative 4 moles of oxygen. So that number is tiny. Get that over there so you can see it. The struggle is real here. Okay, so I have 3 mole values now, okay, for my original compound. I've got this mole value for oxygen, I've got this mole value for carbon, and I've got this mole value for hydrogen. All right, so I'm going to erase some stuff now and rewrite my pseudo formula. Okay. Wait. Almost got that all in there. Okay. I mean, we're going to divide everything by that oxygen value because it's the smallest. Okay. So we're going to divide everything by 6.4625 times 10 to the negative 4. All right. Calculator time. So we can see 9.95 H, let's see, 0.286 divided by 6 times 10, got 19. And oxygen 1. Okay, so this value is within 0.1 of a whole number, so we can call it C10. Same thing with the hydrogen, that's H20, and then we have O. So this is our empirical formula. Okay, we cannot reduce this down any further. But now the next question is, what's our molecular formula? Right, to figure this out, we have to look at the following relationship. If you remember this from class, I think we were still having, or maybe this was the lecture that the first one that we missed. We have this N value that we're looking for, and we're going to find it by putting our molecular formula mass or our molar mass. We're going to divide it by our empirical formula mass. Okay. Now, in questions like this value here, they'll always give that value to you, the molar mass or the molecular formula mass. And they did in this question also. It says, if menthol has a molar mass of 156 grams per mole, what's the molecular formula? So they already told you that our numerator here is going to be 156 grams per mole. Now, this bottom value here our empirical formula mass, we are responsible for finding that from the empirical formula, okay? And we're just going to do that by counting up the molar mass of this compound. So 10 carbons, 20 hydrogens, and 1 oxygen. Let's see what that mass is. It's 156.3. Now, if we divide these, we get something that's very close to 1. The number that you get here, to find the molecular formula, you would multiply your empirical formula by this number to get your molecular formula. So if this value is 1, that means that your empirical formula and your molecular formula are the same formula, which does happen sometimes. Okay? All right. Let's see. Okay, so hopefully that all makes sense to you. I think that we will pause here because it's been like an hour, I guess. And I'll work on making like another part of this where I do some more of the problems. Again, probably not all of them because I'll be here for days, but you know, enough of a sampling of them so that you can work through these on your own also and get some good practice in. Email me if you have any questions, per usual. I'll talk to you soon.